And thing that I forgot to actually include in the last lesson on Le Chatelier's principles, graphs of Le Chatelier's principles. So there are three types of graphs that you need to be able to identify, as well as to interpret. So there's the rate to time graph, and we've kind of drawn it a little bit earlier in the previous lesson, rate versus time graph. The second one would be the, what is it? The mole to time graph. The mole versus time graph. And the last one is your concentration versus time graph. So you need to be able to, all of this Chatelier's graph or Chatelier's principles graph, right? You need to be able to identify them and also be able to interpret what it means. So let us start off with this one. So remember, in this one, it's just on your x-axis you have the time, on your y-axis you have your rate of reaction. And then your reverse reaction will start here, increase, then after a certain time reach a certain constant. Your forward reaction will start there at the top, its rate will be high initially and then drop until it reaches that constant as well. And then here you have your equilibrium, where the rate of the forward reaction, so this is reverse and this is forward. So in his case, the rate of the forward reaction here at equilibrium is equals to the rate of the reverse reaction. And then the mole time graph is more or less similar to this one, right? So on the y-axis, and I'm going to show you two types of them. So on this x-axis, you have your time still in seconds. And then on this side, you have your concentration or your mole. So it can either be one of the two. Concentration is measured in mole per cubic decimeters. Your moles are measured in mole, right? Cool. So you have your reverse reaction maybe from here. Its concentration, it's low at the beginning, but as more product is formed, the concentration increases up until it reaches a certain point where the concentration is no longer changing, or the number of moles is no longer changing. Here you have the highest number of moles of your reactants in the beginning, or the highest concentration. Remember, that's what you're starting with, and then it decreases up until it reaches a certain point where there's no change in concentration or change in mole. So what are you noticing? So here they have reached the equilibrium. The rate is still the same. The rate of the forward and the reverse reaction are the same. However, it doesn't mean that the concentration of the, so here you have your products or your reverse reaction, and then here you have your reactants. So it doesn't mean that it doesn't mean that at equilibrium the number of moles of the reactants or the concentration of the reactants is equals to the number of moles of your products or the concentration of your products, right? Another way in which this can be slightly different than that one. Let me do this. So still trying to draw the same graph. You have your time in seconds, and then you have your concentration or number of moles, right? So here you are, remember at the beginning, this is your products. You have no product at the start, so the product is zero. But then as more reactants are converted into products, your number of products will increase, or your concentration, up until it reaches a constant concentration. Same thing, at the beginning you have a lot of reactants, but then as more reactants are converted back, the number of products will essentially decrease. So this would be your reactants. The number of reactions will be decreased, not increased. And then this is your product. So you see here, It's at equilibrium. At equilibrium, it means the rate of the forward reaction is equals to the rate of the reverse reaction. But it doesn't mean that um just two equate or these two reactants, the forward and the reverse reaction, will have the same number or the same number of concentration or the same number of moles, right? So it's quite important for you to be able to identify these types of graphs and also be able to, what is it I'm thinking, and also be able to interpret them, what is happening. So just to kind of finish off this lesson, I want us to just take a look at one graph that I took from some textbook. So let us say we were given a graph such as this one, and we were told to kind of interpret it. So the first thing you would know is that it is a rate of reaction versus time graph, right? And then they saying the two graphs over there. The straight line is the forward reaction, so that will be 2ab gives us 2a plus b2, right? And then the reverse reaction is the dotted line, means that b2 plus 2a gives us 2ab. So your product is turned back into reactant, right? Cool. So you would say, okay, this is my forward reaction, this is my reverse reaction, right? And then you notice that here, after a certain point, these two reactions are at equilibrium. So the rate of the forward reaction is equals to the rate of the reverse reaction. So this is our first equilibrium. Then something happens at this time here. We don't know after how long, but something happens. We have a spike, and then we see that the rate of the forward reaction increased a little bit, then again decreased up until it reached another equilibrium here. And also the rate of this one also increased from here up until a new equilibrium was reached. So this is the new equilibrium. New, right? Cool. So now, so we see that both rates are affected in the same way. So both the forward and the reverse reaction are affected in the same way. That is, we had an increase. So both the forward reaction increased at this time as well as the reverse reaction. You see there it is increasing, right? Cool. So what do you think could have happened? So this means if we have a situation like this, it means that it could either have been an increase in temperature that affected both rates, or we added a catalyst. And we've spoken a little bit about what is a catalyst in the previous lessons. Because if we increase the pressure or the concentration, only one reaction is normally favored. So just remember that from the previous lesson. But however, we can note another thing. The forward reaction here is increased more than the reverse reaction. So it increased very much in comparison to the reverse reaction, right? So what is this telling us? This is telling me that whatever change that was applied at this time here, it must have been a change in temperature. Why? Because if it was as a result of a catalyst, what a catalyst does is that it makes sure that both the reverse and the I'm thinking both the reverse and the forward reaction are increased equally. So they will both look the same if we had added the catalyst, right? Cool. So what is this telling me? Why is the forward reaction, what is it telling me when the forward reaction increases more? That is telling me something that the forward reaction must be endothermic. It must be the reaction that uses up heat. We've spoken extensively about this in the previous lesson. It must be the reaction that that uses up heat, because when we increase that temperature there, you see that it spikes higher than in comparison to the reverse reaction, right? Cool. So it means that when whatever change in temperature happened, the reaction that was favored was the forward reaction, and it was a reaction that uses heat, meaning the temperature was increased. So at 10, I'm not sure what I'm saying, at this time here, there was a change in temperature that happened, and it was actually an increase in temperature that favored the forward reaction, right? And let us bring this lesson to an end.